Hey everyone, it's Greenland and Arctic climatologist Jason Box here to share some important yet scarcely known ways the Greenland ice is melting faster than we could earlier imagine. Join me on this ablation area safari where you'll be able to see with your own eyes important ways the ice reacts to increasing melt. Greenland is the laboratory, yet the visuals and science findings are also highly relevant for melting land ice around the rest of our world. This video is part of Faster Than Forecast, a new book I'm releasing with a bunch of video at the website sela.cool. With support from the Leonardo DiCaprio Foundation, we flew an autonomous fixed-wing drone over the lowest one-third of the western Greenland ice sheet, where surface melt occurs in increasingly extravagant ways. Western Greenland is where the ice sheet's ablation area is up to 150 kilometers wide. The ice on Greenland contains 7 meters equivalent sea level rise. And now that atmospheric carbon is 50% above pre-industrial times and still increasing, the ice loss currently stands above 8,000 cubic meters per second. The majority of ice sheet mass loss is due to surface melt during summer. And the committed sea level rise means global society needs to get ready for a very expensive tab that has accumulated ever since the true cost of carbon pollution has been externalized from our economic system. But I digress. Let's get into the science. The main purpose of this video, and further detailed in some of my book chapters, is to describe numerous physical mechanisms behind the hypersensitive ice response to climate heating. These mechanisms form the basis of what are called feedbacks. The feedbacks amplify the initial effect of warming. Interestingly, the amplifiers work in reverse. In a cooling scenario, they ensure the expansion of ice. Yet, there's no foreseeable prospect for climate cooling, barring a nuclear winter from a meteor impact or nuclear war. Extensive solar radiation management by stratospheric aerosol injection is indeed a way that people could take the edge off of warming, but it's a temporary prospect, or at least advisable against, for its many governance challenges and possible unintended consequences. Again, I digress. Let's get back to the story the ice is telling. Most of the feedback mechanisms I will present here remain absent from climate model projections of the future. The non-inclusion of the feedbacks is fundamentally why the ice loss is happening faster than forecast. Why the models don't include the mechanisms, I will be describing after I take each of the first 6 amplifying feedbacks in turn. This video focuses on one of the most conspicuous elements of the faster than forecast story told by Greenland ice: surface meltwater lakes. Hundreds of turquoise and sapphire blue meltwater lakes form across the ablation area each summer as meltwater collects in areas without crevasses, surface depressions that are the surface expressions of valleys in the terrain under the ice sheet, hundreds, even thousands of meters below the surface. The lakes appear and persist for days, weeks, even months during the ablation season that runs from about June through August, though of course the duration of the ablation season has been increasing by days and weeks, and is one of the drivers of the numerous feedbacks I'm approaching in this video and in more detail in the book. The largest Greenland surface meltwater lakes are 9 square kilometers in area. That's 3 times the size of Central Park in New York City. The largest lakes contain 50 million cubic meters of meltwater, an amount that hypothetically, from the largest of hundreds of lakes, would give each person on planet Earth 6 liters. I've been studying melt lakes in the field using rafts, and with an echo sounder I could measure the maximum water depth to be 20 meters. That's about as deep as these lakes get. How do I know that? It's because the deepest parts of the lakes were also the darkest points on satellite images. More about that in a bit. Now, in one study, we found that about 1/3 of the western ice sheet lakes drain in under 4 days. The largest single rapid lake drainage we observed delivered 30 million cubic meters of water suddenly into the ice sheet. This one large lake drainage was equivalent with 5 times the flow of the Thames River. Other studies have shown that drainage can occur much faster. And while I knew that the lakes could drain quickly, I gambled that since the lakes persist for days or weeks, and that I'm out there on the lake only a few hours at a time, chances were I'd not be lost into the ice sheet. But from the data I gathered, I was able to map out the correspondence between lake depth and water darkness, and thus measure the volume of water in a given satellite pixel. And so, with that empirical function, I could measure the depths and thus the volume of such lakes across the whole ice sheet ablation area. There's a link to that study in the notes to this video, and more about the drama of the lake rafting appears in the book. Now, finally, to the important points. As the climate warms, the lakes amplify melt in more than 5 ways. 1. The lakes form higher and higher in elevation. 2. Consequently, a larger number of lakes form. 3. The total area and volume of the lakes increase. Because the lakes are dark, the fourth feedback mechanism is the increased absorption of sunlight of the ablation area. The ice sheet darkness, and so the amount of ice melt, increases. One study linked below concluded that already by mid-century, 2050, the lakes will spread another 100 kilometers further inland. The spread of the lakes to higher elevation drives mechanism number 6, involving what is called hypsometry. Hypsometry refers to how the area on an ice sheet expands faster than linearly toward higher elevations. In other words, the surface gets flatter with increasing elevation. Mechanism number 5 involves the rapid drainage that most lakes undergo. We found evidence that the fraction of lakes that drain rapidly increases with warming. That fact could reinforce the role of rapid lake drainage in the deglaciation of Greenland. The lake drainage can remove weight quickly enough from the surface that the change in the stress exceeds the yield strength of the ice. Prior to lake drainage, the ice is in hydrostatic equilibrium. That is, there's a balance between downward gravitational force and the force of the ice pushing back upward. So, in response to the sudden loss of downward force once the lake disappears, the resulting deformation can either be slow, like how cold honey flows, or fast, when the shear strength of the ice is exceeded. The thing is, there's an abundance of pre-existing healed fractures, and so when fracturing occurs, a violent tectonic upheaval of the surface often occurs. The damage allows the water to transmit deeper into the ice sheet. I've not witnessed the destruction of an ice blister in real time in person, but Sam Doyle did, and he talked of being knocked to the ground by the floor shifting abruptly under him. An adept climber, he later rappelled down into the rift for closer look. Now, the drainage floods the bed of the ice sheet, pressurizing it and causing uplift and flow acceleration that Sam's study documented using GPS. The ice speeds up a factor of 3. I guess it's good the effect is only local and for a short while. Nonetheless, the ice moves again a bit closer to the sea. In a warming scenario, the flatter surface amplifies many or all of the feedback elements I'm describing. It's fair to speculate about other feedback processes like the observed wintertime draining of some lakes, or subglacial lakes, or the mineral outcropping that causes dark foliation in the ice sheet's surface. And all of these mechanisms are not yet programmed into models used to predict the future sea level contribution of the Greenland ice sheet. This is why some top ice sheet scientists have complained that the sea level rise figures in the most recent IPCC 6th assessment report may well be underestimated. policy and engineering that is based on misleadingly low sea level rise does not serve society well in dealing with the risks posed by sea level rise in all plausible future climate warming scenarios. Now, why the mechanisms I'm talking about are not yet programmed into the models has to do with the lakes occurring at a finer scale than can be captured by the relatively coarse model grid spacing. It remains too expensive to run models finer than tens of kilometers, even in the finest resolution model cases. But for better or worse, the mechanisms I've described can be approximated by subgrid parameterizations. Yet, training and tuning the parameterizations to be accurate across the relevant time and spatial scales is challenging at best. And the reality often is that the density of observations is insufficient to create robust parameterizations. So even with a parameterization, the result is low fidelity. Another reason these feedbacks are not yet encoded in the models to predict the future melting of the Greenland ice sheet and elsewhere on our planet is the physics are not yet translated into meaningful mathematical expressions. That work, too, is extremely challenging, representing the envelope of modern glaciology. So the advances are not rapid, and again, because the number of scientists on the job is not large, a lot of our cleverest minds instead sell out to Wall Street or to coding the next video games. I'd rather not discourage you from racing into the field of glaciology, but know that there's not a surplus of job posts in the field, like there should be. Apparently because society does not yet support increasing the size of the science academies that we would need to be effective in tackling the high-risk frontiers of natural philosophy. In other videos, I'll take on the many other key mechanisms behind the faster-than-forecast theme, like ice-ocean interactions or the impacts of rainfall on the ice sheet. Until then, have a look at what chapters of the Faster Than Forecast book you're up for reading. The chapters contain more detail and cover more topics from the knowledge that Greenland and Arctic climate have revealed to me and from the broader science community's publications. And do click like, subscribe, and share these videos to help get the word out about specifically how the ice is melting faster than forecast.